Okay, let us quickly recall what we have discussed in the last class. We discussed singular point of a function. For a complex function, we say a point is a singular point. When f is not analytic at that point, and in every neighborhood there is at least one point at which f is analytic, then I say that point is an analytic point. And we saw some examples for z, f of z equal to 1 by 1 minus z, or z minus 1. The singular point is 1. And for the second example, singular points are 0 and 1. And when it comes to these functions, real part of z, imaginary part of z, and mod z square, these are nowhere analytic functions, so no need of talking about singular points. So there are no singular points for real part of z, imaginary part of z, and mod z square. And we saw some basic expansions. No, before expansions, we saw what are the singular points of sin z by z square, and sin z by z power 4. For all these three functions, we have 0 as a singular point, but its nature is different. First singularity, it comes under one case, and next one it is different, and next one it is different. And when you look at sine of 1 by z, here also singularity is z equal to 0, but it has a different nature. Right? We are going to classify the singularities into removable singularity and pole of order m, and similarly essential singularity. These are the three classifications we are going to see based on the Laurent series expansions. Today we are going to see what is a Laurent series expansion of a given function. And then we discuss Stylus Theorem, which enable us to write a Taylor series expansion of a function in a domain where f is analytic. So if you want to construct a Taylor series expansion for a function about a point, first f must be analytic at that point, and you should be able to find a neighborhood around that point at which the function is analytic. And you can take any large neighborhood such that no singular point comes into that neighborhood. You can choose such a neighborhood. So now the maximum radius of that neighborhood in which the no singular point is coming, that's what we call the radius of convergence of the power series centered at z0. Suppose if the singularity is here, let's say this z prime is a singular point. Now and let us assume that this is the nearest singularity from z0, then the radius of convergence of the obtained power series is going to be this. This will be the radius of convergence. So without writing power series expansions, we can conclude what will be the radius of their convergence simply by looking at the distance between the center and the nearest singularity. This Stylus theorem says that when you have an analytic function in an open disk, if you write a Taylor series expansion or a series expansion, then an must be equal to nth derivative at z0 by n factorial. And we found what will be the radius of convergence for this function, and then some basic series expansions. Then we saw the expansion for sin z, cos z, e power z. These are all entire functions, which means these functions are analytic everywhere on the complex plane. So the validity of this expansion is going to be the entire complex plane, that is mod z less than infinite. Therefore the radius of convergence will be infinite. And at the end I gave you this problem. I asked you to write an expansion of f of z about 5. And if you write an expansion, we know what will be its radius of convergence. Radius of convergence is 7. Why? Because the singularity of this function is 2, and the distance between 2 and negative 5, which is 7. So this will be the radius of convergence of this series. So only thing you need to find what are an's here. So let us try to obtain what is an. What is the function? Z plus 1 by z minus 2. Okay. So the function here is f of z equal to z plus 1 by z minus 2, and we want to write a series expansion, that is summation an into z plus 5 whole power n. Now the question here is, what is an? So let us try to obtain this. So first, let me change the denominator with this term, that is z plus 5. So let me write it like z plus 5. If you want z minus 2, then you should subtract 7 from here. Now this equal to, now I'd like to simplify the numerator as well. I'd like to express in terms of z plus 5. So z plus 5 minus 4. And in the denominator I have z plus 5 minus 7. So now this z plus 5 minus 4, I'll keep it at side. Now first I'll think about this guy, that is 1 divided by z plus 5 minus 7. I need an expansion which involves the term z plus 5. So I wrote it this way. Now from this term, so now let me concentrate on this term only. Why to write every time this guy? So let me start with this function. 1 divided by z plus 5 minus 7. So you can take 1 by 7 out. Then you have, let me take minus negative 1 by 7 out. So I'll have 1 minus of z plus 5 by 7. Now it is in this form, 1 by 1 minus x. We know what is its expansion. So negative 1 by 7, this is summation n equal to 0 to infinite. So the expansion here is z plus 5 by 7 whole power n. The expansion of 1 by 1 minus x is summation x power n. Now you can take this negative 1 by 7 inside of this function. Then now let me write what is f of z directly. F of z equal to z plus 5 minus 4, this multiplied with summation n equal to 0 to infinite. I have z plus 5 whole power n by 7 to the power of n plus 1 minus. Now you can multiply with z plus 5. So when you multiply with z plus 5, summation n equal to 0 to infinite. So you have z plus 5 whole to the power of n plus 1. This term is anyway common. So let me write negative 1 by 7 to the power of n plus 1. This is common. Now when you multiply with this guy, which is z plus 5 whole to the power of n plus 1 minus 4 into z plus 5 whole power n. Okay, but if you want to write it as a single term, you can do one thing. See, instead of doing all this, initially if we apply the division here, this one can be written as z minus 2. The numerator can be written as z minus 2 plus 3. So 1 minus negative 3 by z minus 2. So 1 minus of, it is enough to write the expansion of this. Why? Because I'd like to find what exactly an is, but if I write it like this, can I find what is an? What you can take z plus 5 whole power n common, then you'll be left with z plus 1. But I want to have a term that has only z plus 5 only. I don't want to express it as two summations. I want a single summation. And let me do one thing. Let me expand this instead of going all this way. So anyway, we have seen what is the expansion of 1 by z plus 5 minus 7. Okay. So this we did, 1 by z plus 5 negative 7. This we did. Let me continue here. Now f of z equal to, I can write it as 1 minus 3 by z minus 2, which is 1 minus 3 times of okay, let me write minus 1 by 7 summation n equal to 0 to infinite z plus 5 whole power n by 7 power n. So 1 minus into minus plus summation n equal to 0 to infinite. You can take this 3 inside. So 3 by 7 to the power of n plus 1 into z plus 5 whole power n. Okay, so now this is the power series expansion of f of z in terms of z plus 5 whole power n. So here we got one constant term extra, or let me write it like this. The constant term here is 1 plus, when you substitute n equal to 0, you'll get 3 by 7, 1 plus 3 by 7, that will be 10 by 7. This is the constant term, and the rest will be same as this. N equal to 1 to infinite, 3 by 7 power n plus 1 into z plus 5 whole power n. So this is what our function is. I mean, series expansion of the given function. So if you ask me what is a naught is nothing but 10 by 7. And what is a1? a1 is the coefficient of z plus 5. So you need to substitute n equal to 1. That is 3 by 7 square. This is a1. And a2, which is 3 by 7 cube and all. Okay. Whereas let us see what happens in the other expansion. This is correct, right? 1 minus 3 by z plus 2, z minus 2, z minus 2. Oh my god. I want plus 1, z minus 2, then I should write plus here. If I write plus, then only I get z plus 1 in the numerator. So if it is plus, then it must be plus, then it must be a positive, then it will be a negative number. Yeah, now there's a change. So 1 minus 3 by 7, so which will be 4 by 7. Yeah, now a naught will be 4 by 7 and a1, that is 3 by 7 square, negative 3 by 7 square. Why? Because you have negative here, negative 3 by 7 cube. So this is a2. And let us see what is a naught, a1, a2 from this expansion. Okay, so if you want a naught, that is the constant term you'll obtain when you substitute n equal to 0 here, only this term. Okay, when you substitute n equal to 0, see, try to understand one thing. We need a constant term in the entire expansion. Okay, so the only constant term you can get it here, that is negative 4 by 7. I hope you can see that. And if you want a1, that is the coefficient of z plus 5, and z plus 5 will obtain when you plug in 0 here, when you plug in 1 here. Okay, so if you see the coefficient for this, that is negative 1 by 7 square, whereas if you look at the, this will get when we substitute n equal to 1. So negative 4 by 7. Now you take LCM. The LCM is nothing but 7 square. Now this is negative 1 minus, it seems we got something wrong. I'm not getting negative 3 by 7 square, but here we got negative 3 by 7 square. So what is it wrong? Oh yeah, this one, it is actually 1, and this is actually square. Now we'll get the result. So now when you take LCM, 7 square is the LCM, and minus into minus, this will be plus. So negative 7 plus 4, so this will be negative 3 by 7 square. So a naught is negative 4 by 7, a1 is negative 3 by 7 square. And look at a2. a2, that is the coefficient of z plus 5 whole square, and when n equal to 2 here, and when n equal to 1 here. So be careful. negative 1 by, this is what when 1, 7 square, minus into minus, plus 4 by, you get 7 cube. So this is same as negative 3 by 7 cube. Okay, so whatever coefficients we are getting here and here, both are same, they are not different. Both expansions are correct. But here it is easy to recognize an, but whereas here, yeah, you can do some work and you can get into this form. Where is it? This form. Okay, so let us look at another problem of this kind. Given f of z equal to 1 divided by z, 1 by z. Now I need Taylor series expansion of f of z. Yeah, tell me one thing, is it possible to find series expansion of f of z which is of this form, that is f of z equal to summation n equal to 0 to infinite an into z minus 1 whole power n? Is it possible to find series expansion of this function of this form? If so, what is the radius of convergence? Now first of all, you need to see what are the singular points of the function. Singular points of f are z equal to 0. That is the only singular point. Okay. Now they are asking us to write a series expansion centered at 1. So let me look at the complex plane. This one, x-axis and then the y-axis, and then z equal to 1, which will be here, whereas the singularity, that is z equal to 0, which will be here. Now is it possible to create an open disk around z equal to 1 so that it does not include any singular point? Is it possible to draw a neighborhood around 1? If so, what is the maximum radius of that neighborhood so that no singular points comes inside it? It is 1. The radius of the neighborhood around 1, that maximum it can be 1. Okay. So now answer to this question is yes, it is possible. Now r equal to 1, the radius of convergence is going to be 1. Now let us see how to obtain that expansion. So you start with the function f of z, which is equal to 1 by z, but I want to have z minus 1. So let me write z minus 1 plus 1. So this is equal to 1 by, you can take negative common, so 1 minus of z minus 1. Is that correct? Then I get negative z. Then I should have z plus 1 here. So plus. Then in that case, why to take negative out? No need. So this one can be written as 1 by 1 plus z. And we know what is the expansion of 1 by 1 plus z. That is what 1 minus z plus z square minus z cube plus and so on. In other words, this is nothing but summation n equal to 0 to infinite minus z whole to the power of n. This is the formula. So using this formula, I can say the power series expansion of this is summation n equal to 0 to infinite minus of z minus 1 whole to the power of n. So this is nothing but summation n equal to 0 to infinite minus 1 to the power of n into z minus 1 whole power n. Now if you ask me what is an in the power series expansion, an is nothing but negative 1 to the power of n. And the radius of convergence, so radius of convergence r is equal to 1. Why? Because you can see the distance between the singularity and the given point. Okay, so this is how we are going to obtain Taylor series expansions. Okay. Now the next question is, so we got the expansion in this region, that is mod z is less than 1. Now, mod z minus 1 is less than 1. This region is nothing but mod z minus 1 is less than 1. Now I'd like to know what is the expansion if mod z minus 1 is greater than 1. Can we have an expansion in this region? If so, what will be that? Or let me ask it for a different question. Let us take the standard one, that is 1 by 1 minus z. You know the expansion here, summation z to the power of n equal to 0 to infinite. You know that it is valid only when mod z is strictly less than 1. And here I have the y-axis and x-axis, and this is origin. And the singularity of this function is here, which is z equal to 1. Now this is an expansion centered at 0. So let me draw a neighborhood centered at 0, which does not include any singular point. So this is the neighborhood. This is the maximum possible neighborhood. Okay, and we are going to denote it like mod z is strictly less than 1. Now, I want to know what is the series expansion when mod z is greater than 1. When less than 1 we know, when greater than 1 we'd like to know the expansion. So let me do one thing, let's take f of z. So what I have is mod z is greater than 1. I want to derive series expansion in this region when mod z is greater than 1. The given function is this 1 by 1 minus z. Okay. So when mod z is greater than 1, can I say this implies 1 divided by mod z, which is less than 1? If mod z is greater than 1, then its reciprocal will be less than 1. Okay. So now you know the reciprocal is less than 1. Now using this formula, so try to get 1 by 1 minus z, and using this formula you can write the expansion. I mean, instead of having z, if you have 1 by z, then I can use this formula, whatever expansion you have it here. So let's do one thing. For that, let me take 1 by z common from this entire thing. When you do that, this is 1 divided by 1 by z minus 1. Isn't it? Now let me take negative common. So negative 1 by z. Then I have this 1 by 1 minus of 1 by z. Okay. Now it is in this form 1 by 1 minus x, where absolute value of x is less than 1. You can see that. From this I can say absolute value of 1 by z, which is less than 1. It means now I can apply this expansion. So this is negative 1 by z into summation n equal to 0 to infinite. So this is 1 by z whole power n. Now this equal to summation n equal to 0 to infinite minus of 1 by z power n plus 1. Okay. Now this is the series expansion of 1 by 1 minus z when mod z is greater than 1. Now you see, when mod z is less than 1, we have an expansion. That is what exactly Taylor series expansion, polynomial expansion. But when mod z is greater than 1, there also you have an expansion. But this is not Taylor series expansion. Why? Because we do not have polynomial functions here. What we have is the reciprocal of the polynomial, 1 by z power n, 1 by z power n plus 1. Okay, and this series expansion is called as a Lorent series expansion. And of course, Laurent derived how to get a series expansion when you go beyond the singularities. So let us look at what Lorent theorem says. So here is the Lorent theorem. So try to understand what this theorem says. You have a function f which is analytic throughout an annular domain. Annular domain, we mean the region between the two circles. You see, this is the region. Let's say this is circle 1 and this is circle 2, and region between these two circles, which is called an annular region. Okay. So in this annular region, the function is analytic. and this annular region which is actually centered at z0, so the center is z0. Okay, and you start with any curve which lies in this annular region, and also it is closed. And the main important thing is this curve should, that z0 must be an interior point of that curve. That is one of the important thing you need to note down. Z0 must be an interior point of the curve. Okay, so and let's see denote the positively oriented simple closed contour around z0 and lying in the domain, where domain is this. Then at each point in the domain, f of z has a series representation, and the series representation will be given by this formula. And if you observe this part, this is actually an analytic part. It means, it is a polynomial function, no? Polynomial function is always analytic. Okay, so that's why it is called an analytic part. So this is the possible Taylor series expansion, plus we have other terms here which are not polynomials, but you are exactly taking the reciprocal of 1 by z minus z naught. So that's what you are doing here. So bn divided by z minus z naught whole power n. Now how to obtain these coefficients an and bn? So now an can be obtained by this formula. If you observe that this is nothing but a Cauchy integral formula. Okay, so using Cauchy integral formula, what do we know? This is actually, the value of this integral is nothing but nth derivative at z0 divided by n factorial. 2 pi I we have written here, so no need of writing it here. So when you write a Taylor series expansion, an is same, right? Nth derivative at z0 by n factorial. That is what an in the Taylor series expansion. Of course, we are writing the same here, but with the help of Cauchy integral formula. Now this will help you to find bn. Now bn is going to be this, that is f of z by z minus z naught whole to the power of negative n plus 1. Okay, but here I cannot write negative nth derivative. What do we mean by negative nth derivative? There is nothing like that. Okay. So now if you look at the previous example, f of z equal to 1 by 1 minus z, this function has a Taylor series expansion when mod z is less than 1. Okay, whereas when mod z is greater than 1, this is going to have Lorent series expansion, and this is the Lorent series expansion. Okay, now let us look at another function. If you have f of z equal to sin z by z power 4. Now the question is, find Lorent series expansion. Find Lorent series expansion of f of z. Okay, I should tell you about what point. So the Lorent series expansion of f of z about z equal to 0. It means I need an expansion which is centered at 0 only. And you should understand this theorem statement. If you observe that this Stylus series is, the Lorent series is actually centered at z0 only. Okay. Now let us see what are the singular points of f of z. Singular point of f of z, that is 0 only, because z equal to 0 is the only singularity of this function. Now I need an expansion about z equal to 0, but I'll do one thing. I know what is the expansion of sin z. So let us write that expansion. We know sin z equal to z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. And you know this expansion is valid for every z belongs to R. Sorry, for every z belongs to C. Okay, in other words, you can write it as mod z is strictly less than infinite. This expansion is valid for it. when mod z is strictly less than infinite. But the moment if you look at sine z by z, sine z by z, z power 4, which is actually 1 by z power 4 into sine z. And you know the expansion of sine z in terms of z. So let us write that expansion. So 1 by z power 4, this into z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. Okay, but when it comes to the validity, you know this expansion is valid when mod z is less than infinite. That is fine. But 1 by z power 4 is not defined at 0. So we should exclude 0 from the validity. So 0 is strictly less than. Now when you multiply with 1 by z power 4, so the first term here is 1 by z cube minus 1 by 3 factorial into 1 by z square plus z by 5 factorial minus z cube by 7 factorial plus and so on. Now you see we have infinitely many terms in the analytic part. This is the analytic part. Okay, in the other part you have only 2 terms. Now this is the Laurent series expansion of the given function, and let us write it using formula, summation notation. If you use summation notation, this is actually 1 by z power 4 into summation n equal to 0 to infinite negative 1 to the power of n plus 1 into z to the power of 2n plus 1 by 2n plus 1 factorial. So the moment you multiply with 1 by z power 4, this is what I'll get. N equal to 0 to infinite negative 1 to the power of n plus 1, and this is z to the power of 2n minus 3 by 2n plus 1 factorial. Okay, and let me clearly write 1 by z cube minus 1 by 3 factorial into z square plus, now the rest of the thing I'm going to write it like this: n equal to, when n is 0 you get this, when n is 1 you get this, so n equal to 2 to infinite negative 1 to the power of n plus 1 into z to the power of 2n minus 3 by 2n plus 1 factorial. And if you want to start with n equal to 0, you can start, but you need to change this index. So when n equal to 2, you are getting 1. So okay, let me make that change. So sine z by z power 4, which can be expressed as 1 by z power 4 minus 1 by 3 factorial into z square. Am I correct? Oh, z cube is 1, and another one, how I get z square here? This is supposed to be z only, no? The denominator. This must be z. Yeah. So this must be z. Plus summation n equal to 0 to infinite. Now I'll do one thing. I'll plug in n minus 2 equal to m. When I do that, this 2n minus 3, it will become n equal to m plus 2. So this is m plus 2 negative 3. So this is 2m plus 1. And when it comes to 2n plus 1, you'll get m plus 2, 4, so 5. M plus 2 plus 1, so 2m plus 5. So this is negative 1 to the power of n and this is z to the power of 2n plus 1 by 2n plus 5 factorial. Okay, so this is what exactly the Laurent series expansion of sin z. Okay, and this expansion is valid when 0 less than mod z less than infinite. So if you compare with Laurent series expansion, can you tell me what is b1 here? You see the Laurent series expansion is here. b1, that is the coefficient of 1 by z minus z naught. It means here it is the coefficient of 1 by z, so that is 1 by 3 factorial. And if you see what is, this should be z cube. If you see what is b2, b2 is 0 because there is no 1 by z square term, and b3 which is 1. And here in this expansion, if you see what is an in the Stylus series expansion, that is negative 1 to the power of n plus 1 into, this by 2n plus 5 factorial. This is what an is. Okay. See, mostly to derive Laurent series expansion, we don't use these formulas. We'll write the expansion from the known formulas itself. Okay, while calculating residues only, we may take help of this formula. Let's do one thing. Let us solve one more example. So let us see what is the Laurent series expansion, or what are the all possible expansions of this function in all domains. So I need all possible expansions about 0. About z equal to 0, I need it. Okay. So first you do one thing, you try to recognize what are the singular points of this function. The singular point of this function is z equal to negative 5. Z equal to negative 5 is the singular point. Now I want to write the expansions about 0. So the center of the expansion is 0. So now one possibility is this. Here we are going to have Stylus series expansion. Why? Because f is analytic. Okay, and whereas here out of this circle you are going to have Laurent series expansion. So first let us write what is this region, which is mod z is less than 5. So let me write the region 1 when mod z is less than 5. Now the expansion is nothing but f of z equal to 1 by z plus 5. You can take 5 common, 1 by 5 common. So 1 by, you'll have 1 plus z by 5. Okay, when mod z is less than 5, that implies modulus of z by 5. This is less than 1. Now I can apply this formula 1 by 1 plus x. When mod x is less than 1, we can write the expansion. So this is summation n equal to 0 to infinite z plus 5 whole power n into minus 1 to the power of n. Maybe let me write this directly, minus z by 5 whole power n. That's it. So this is the series expansion of the function when mod z is strictly less than 5. Or you can write it as n equal to 0 to infinite negative 1 to the power of n by 5 to the power of n plus 1 into z to the power of n. This is what when mod z is strictly less than 5. And let us look at the other expansion, that is in the region when mod z is greater than 5. Mod z is greater than 5, this implies mod z by 5 which is greater than 1. Now that implies phi divided by mod z, which is less than 1. Or in other words, let me write it, modulus of phi by z, which is strictly less than 1. Now using this fact to know the expansion of f of z, so let me start with z plus phi. This time you take z common. When you take z common, you'll have 1 plus phi by z. Okay. Since you know phi by z is strictly less than 1, its absolute value is strictly less than 1, then you can write its expansion. So let us write it. So 1 by z, this is summation n equal to 0 to infinite. I have minus phi by z whole power n. In other words, f of z equal to summation n equal to 0 to infinite. You can take 1 by z to the inside. So minus phi to the power of n by z power n plus 1. And this is the expansion valid in the region when mod z is greater than 5. Okay, so this is the Laurent series expansion in the region mod z is greater than 5. And whereas the Stylus series expansion when mod z is less than 5 is this. Okay. So in the next class we'll solve few more problems, like what happens if you have f of z equal to 1 by z minus 1 into z minus 2. Now this time there are two singular points, not just one. Okay, so we'll look at this problem in the next class. And you do one thing, you take it as a homework. If we take f of z equal to 1 by z minus 3, write all possible series expansions. One is the Stylus series expansion, another one is the Laurent series expansion. Okay, about 0. And this is 1, and the second about z equal to 1. So I need 2, not just 1. About z equal to 1 is 1, and about z equal to 0 is another. Okay, so this is first problem, and the second problem, f of z equal to sine z by z. F of z equal to sine z by z. And next, f of z equal to cos z by z power 4. So take these three problems as homework. All that you need to do is you need to write series expansions, Laurent series expansion of these functions. Okay. Okay, then I'll stop it here. Let me know if you have any questions or doubts. Okay, so we'll meet in the next class. Bye.